Hi, my name is Kylie Hughes, and today I'll be telling you about my research project. The goal of this study was to evaluate the hydrological differences between soils impacted by existing earthworm species and the newer, more invasive jumping worms in Minnesota forested environments. First, let's get some background for this topic. Asian jumping worms are an invasive species first discovered in Minnesota in 2006. Technically, all earthworms are invasive to Minnesota due to a recent glaciation, but established species like nightcrawlers burrow and therefore distribute their impacts across the entire soil profile. Jumping worms, on the other hand, do not burrow and live exclusively in the top layer of soil, so their impact is concentrated at the soil surface. Their presence leads to an increase in pore space and organic matter, replacing the typical A horizon with a loose, granular morphology. You can see the aggregates that create this excess pore space in the image in the top right. Data for this experiment was collected using MPD infiltrometers. 40 samples were taken in a landscape of ongoing jumping worm invasion. The first site contained exclusively nightcrawlers. The second location was a site where jumping worms were encroaching on a previously nightcrawler-dominated area, and the third site was dominated entirely by jumping worms. Now let's look at some graphs of this data. The drainage rates of all sites were then documented in this graph of centimeters over time. For all graphs, the blue dots represent nightcrawlers, the green dots represent the intermediary location, and the red dots represent jumping worms. This graph is a great visual representation of just how different the drainage rates were. As we can see up here in this top graph, the nightcrawlers drained much slower than either of the jumping worm locations. It was truly exponential. It was scary to watch. To put this difference into perspective, the longest completed nightcrawler measurement took 8.5 hours, and the shortest jumping worm was 17 minutes. If we look at this top red line up here, we will see that there is an outlier in the jumping worm data. This plot drained at a rate 7 times slower than the average of the other jumping worm samples. When we dug into the soil where the sample was taken, we found a large clay deposit that was not present in the rest of the test locations. This indicates that the slow drainage at this site was probably due to an obstruction in the soil unrelated to jumping worm presence. The next step in quantifying the hydrological differences was to find the saturated hydraulic conductivity, or the KSAT, of each sample. The KSAT is a measure of a soil's ability to move water when fully saturated, and it tells us a lot about the hydrologic characteristics of a soil. The KSAT of each sample was calculated by fitting them with a second-degree polynomial formula and accounting for how much soil moisture changed during each test. The calculated values were then averaged across each test location to create the table we see in the bottom right here. The KSAT of the jumping worm plot was found to be 13.3 centimeters per hour, which is more than 5 times higher than the nightcrawler value of 2.5 centimeters per hour. This higher value indicates that the water moves through the soil much faster, which could lead to lower plant available water, changes in water table, and changes in undergrowth vegetation. This value was also used to calculate the standard error. The jumping worm samples had much lower relative standard errors, with an average value of 15.3% compared to the nightcrawler's value of 40.4%. This indicates that the samples were draining at a much more uniform rate, which is concerning because variations in drainage patterns are essential to supporting ecosystem biodiversity. Variation in soil characteristics in a typical soil, like the one we see in the nightcrawler plot, create different sections with different amounts of plant available water and microbial activity, allowing many species with varying ecosystem needs to live in the same location. Removing this variation greatly reduces the number of plants that can survive in a given area. The next graph I created was a graph of velocity over time. The graph shows that jumping worms have significantly higher initial velocities and consistently higher velocities throughout the entirety of drainage. This result is also concerning because higher drainage velocities lead to increased nutrient leaching. This is because the faster that runoff drains, the less time it has in contact with the soil surface, and the less time it will have for nutrients to be absorbed or filtered by the soil. Additionally, nutrient leaching has led to decreased soil fertility and pollution of groundwater with compounds like nitrates. Obviously, nitrates are very bad for human health. These changes are particularly concerning in Minnesota ecosystems, as Minnesota is the headwaters for the Mississippi River and is also the third largest corn producer in the United States. Corn is infamous for its excessive nitrogen runoff, and its cultivation contributes significantly to the Gulf of Mexico dead zone. As jumping worms continue to strip Minnesota soils of their A horizons, these issues will only continue to get worse. The final graph I created was a graph of acceleration over time. This graph did not show much significant difference between jumping worm and nightcrawler values, so we're not going to talk about it much. In conclusion, soils impacted by jumping worms have higher drainage rates and velocities than soils impacted by nightcrawlers, increasing nutrient leaching and decreasing plant available water. The lack of variation in drainage rates for soils impacted by jumping worms with lower biodiversity and threatened habitat for many forest animals. Due to all of these factors, the continued spread of jumping worms threatens soil fertility, human health, and numerous aquatic environments. Thank you so much for your time and attention. Have a great day.